Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome to Chibuli Secondary School. Mr. Kando is your presenter for today. Continuing with our study of electrostatics. Today is going to be the conclusion of this topic. And previously, we were talking about the lightning conductor, and we also concluded when we were talking about the ice spell experiment. Now, what is the essence of this ice spell experiment? We had previously talked about charge distribution on conductors. We talked about hollow conductors, and we concluded that inside the charged conductor, hollow conductor, resides no charge, and charge concentrates on the outside. Now, Faraday's ice spell experiment, its intention is to verify that claim that we talked about previously. Here is how the experiment goes. So what we do, we get a tall metal can. And the metal can, we connect it to we rest it on the cap of the gold leaf electroscope. We ensure that at the start, the electroscope is a neutral one. Because if it had charge, then we will claim that the charge was already present on the electroscope. So, then we bring a metal sphere which is positively charged and insulated at the top, which is acting as a handle. Now, if we place it inside the conductor and then we connect it to the gold leaf electroscope, we end up realizing that the leaf diverges. And you know what divergence means? It implies that charge has descended on the outside surface and therefore has caused it to diverge. Then, the metal sphere is withdrawn from the can. We end up realizing that the gold leaf collapses. Once it collapses, it implies that charge is no longer there, meaning that what caused the divergence initially was the presence of the positive charge inside the can. Now we do it third time. The metal sphere is lowered in the metal can, but without touching the inside, and the leaf is seen to diverge by the same magnitude. Before it diverged, and then it is diverging with the same magnitude. The metal sphere is meant to touch the inside of the can. This time around, we'll allow it to touch the inside of the can and see what happens with the divergence of the leaf. We end up realizing that the divergence is not affected. Now, when the metal sphere is taken near the cap of another neutral electroscope, it is found with no charge. Now, where did our charge go? Conclusion. A charged ball, this is what we said the other time, that a charged ball induces equal and opposite charge on the outside of the sphere. And how does that one arise? If this is the ball positively charged, this one is going to induce a negative charge here. But the negative charge produced here will induce a positive charge here. So once this surface is connected to a gold leaf electroscope, the leaf will diverge. But once it is suspended there within the conductor, the charge is temporary on the surface. The charge is what? temporarily on the surface. Now, once we allow this one to touch the surface, then the negative charge neutralizes the positive charges on the sphere, like this. Now, since they are equal in magnitude, the body, the positively charged body, remains with no charge. All the positive charges are neutralized. Are you getting it? That's why when we take this positive charged body to a neutral electroscope, the electroscope collapses. And the collapse of our electroscope, it implies that it has lost all the charge. The second thing we learned is that inside the hollow conductor, the resultant charge inside is zero because the positive and negative charges have neutralized. So bulb B once removed has no charge because the positive charges neutralize the induced charge on the inside of the can. Now let's look at the question answer. There is a question that you have given. If you can closely look at the diagram, we have this time round a negative charge, negatively charged sphere. The negatively charged sphere put in a spherical container, hollow container, and then insulated down to avoid leakage of charge. So it is a dull surface. Now we are saying figure shows a negatively charged metal ball B. Metal ball is B. Inside a hollow metal conductor P. The metal conductor is P. Resting on an insulator. This is an insulator. Resting on an insulator. Now the question is, describe the distribution of charge on the metal conductor. Sorry, not metal. On the metal conductor. P is a metal conductor. B is a metal ball. And then the question is, describe the distribution of charge on the metal conductor. Now we wonder, how will the charge distribute? How will the charge distribute? For those who are around, what is your prediction? How do you expect the charge to get distributed? Pardon? Towards the insulator. No. The purpose of the insulator is to prevent leakage of charge from a peak to the ground. Are you getting it? But the question is asking, describe the distribution of charge on the metal conductor. Once you place a negatively charged body inside the metal, the hollow conductor P, what will happen? How will the charge distribute? Okay. Members, we are going to approach this question in two ways. There is before B touches the P. Because initially in the Faraday's ice experiment, there is when it is suspended and then when it touches. So there are two cases. B is the metal. B is the metal. And then P is the hollow conductor. How will the charge? We are going to classify it into the before B touches P. What will happen? That inside P, we are going to develop a charge when we bring a negative. Remember here, when you brought positive, we developed a negative. And what is your prediction if you bring a negative now this time round? Yes. Inside a hollow metal conductor, a positive charge will be induced on the inside, and a negative charge is going to be induced on the outside with the same magnitude of charge as that on what? B. I'm saying that before B touches P, before B touches P, a positive charge is induced on the inside of these markers, and a negative charge on the outside of P. We are saying the charge on either side is of the same magnitude. Magnitude I mean size, as that on B. Now, if for example the negative charges were two column charge, we are going to produce two positive column and two negative column. The magnitude is the same. That one okay. That is before. Now, what if it touches? What if it now touches? After touching B, after touching B, after touching. In other words, after B touching A, B touching P. After B touching P. What do you think will happen? What do you think will happen when B touches P? Will become what? Ah, sure. Yes. Yes. Inside, it is going to have no charge because B is going to be neutralized by the surface charge that is opposite. Are you getting it? So you're saying B loses all the charge to P. B loses all the charge to P. The B loses all the charge to P. That means the inside of P is not going to be charged. The inside of P is not charged. While on the outside, but the outside acquires a charge equal to that previous one B. But the outside acquires charge of charge equal to that previous one B. Previously on B. Why? Because when this negative, when the negative is here, it induces a positive inside and a negative here. Once this one touches here, the negative is neutralized. But the negative outside had already been registered there. Are you getting it? So by the time you remove this one, the negative charge will be already there on the outside. So that's why he said B loses all the charge to P. The inside of P is not charged, but the outside acquires charge equal to that of that previously on what? B. In other words, the outside will going to acquire a negative charge. That one, okay. Which charge was previously on B? Now we got our last part of electrostatics, that is electric fields. Electric fields. Now, electric fields is just a region around a charge or charged body where electrostatic forces are experienced. The region around a charged body where electrostatic forces are experienced. Electric fields may be represented by field lines. These electric fields, we can't see it by our own, by the naked eyes. But due to their effects, we know they exist. And therefore, we represent them by field lines. These field lines are just visualizations to tell the effect of the field. Therefore, we define electric field line is just a path which a positive charge will follow when placed in an electric field. Like, for example, if we have a positive charge here, definitely it is going to produce a field, but the field will not be able to see. So, we represent the field by using field lines. Using field lines. And we prefer to use a positive charge because the positive charges are the ones that are moving from the surface. So therefore, we are defining an electric field line as a path which a positive charge would follow when placed in an electric field. Properties of electric field lines. 1. They begin and end with equal quantities of charge, meaning that the charge it started with is the same charge it carries up to where it's going. 2. They are in a state of tension, which causes them to shorten. Like, for example, if there were two fields, there is a charge here, when there is a charge here, for example, and another charge here, this one tends, by law of electrostatics, this tends to be attracted to that one. And therefore, this one, like this, and that one, now there is a way they are stretched. There's a what? They are stretched, making them what? Shorten. So that is the second characteristic. 3. they repel each other sideways. You would have expected that since it is a straight line, there is a charge here and there is a charge here. All of them would have moved like this. No, they will not move like that because since both of them are positive charges moving, by law of electrostatics, the positive and positives tend to repel. And therefore they repel each other sideways. That's why when we draw a line like this one, the next one is curved upwards and another one is curved downwards, meaning that they repel each other sideways. 2, that is 4. They meet or leave a charged surface at right angle. They meet or leave a charged surface at right what? Angle. At any time it reaches the surface, it is reaching at right angle. That is 90 degrees. It is reaching at right angle. Then 3, they always point outwards from the positive charge and inwards from the negative charge. In other words, the field lines move from positive to negative, whereas the negatives, it is pointing towards the negative and pointing away from the positive charge. Now, how are the field patterns going to be drawn in such a case? We are going to have field patterns for the different cases. We are going to begin with the isolated case. So isolated cases, part A. We have them on the screen. Isolated cases. So isolated, we have the 2 cases, the positive and the negative. Positive charge and then negative charge. Now, for the positive charge, it's going to be very easy. You just draw a positive and ensure that the fields are moving away from the positive at right angles. Even those ones at an angle like that, they're still moving at right angle. We draw them like this. That is isolated positive charge. Isolated negative charge is the same thing, only the direction changes. It is only the direction that changes, but the pattern is the same. Now you need to know, when we are drawing field lines, we are looking for 3 items or 4.
The negatives coming inside.
Hey, sorry. The negatives are coming inside. Thank you for that observation. The positives are moving away, the negatives are coming closer. Now you need to know when you are drawing these patterns, 3 items have to come in your mind. 1, direction of the electric field. 2, pattern of the electric field. 3, position of the neutral point, if any. And 4, magnitude of the electric field. And the magnitude of the electric field is represented by the number of field lines. Now, for example, if we draw 10 field lines, and the other side we draw 5 field lines, it implies that the magnitude of charge on the 10 is much more higher than that on the 1. Now, like charges close to each other. Like charges close to each other, that means if we have positive and positive charges that are closer to each other, positive and positive. If they are like charges, these ones are going to be repelling. Remember, this field is coming, this one is moving in that direction, another one is moving in that direction. Because of repulsion, that is going to be moving in that direction. So we are going to create a neutral point there. So at the neutral point, the resultant electric field is zero, because the field would have wanted to pass through that point, but it is being opposed by the field from the other side, because this one would have ideally wanted to come, and this one would also have wanted to come. The fact that at that certain point they are equal and opposite. When I say equal, I say equal in magnitude, but opposite in direction. So these ones do cancel each other, such that the resultant field around here is zero. And therefore, that is called in the position of the neutral point. Now, if there are negative charges, the pattern is going to be the same, but the direction is the only one that is going to change. Like we have in our small notes there, we indicated only the negative charge because the patterns are the same. Negative, negative, they are like charges. The shape or pattern is going to be the same. And therefore, it is going to create a neutral point. So here, note, we are very careful about the direction. It's now inwards. Direction is inwards, like that. Now the number of field lines just tells the amount of charge it has. When there are more charges, the number of field lines will be many and the pattern will be congested. If the field lines are few, so it may be as simple as that. But if there are many, it could be as you see the pattern. So that one calls for the definition of a neutral point. So we are saying a neutral point is a region in an electric field where the resultant electrostatic force is zero. Where the resultant electrostatic force is zero. And we said at that point, the field lines cancel each other, and therefore no resultant electric forces exist at that point. So that's how we define the neutral point. Now, fields between charged particles and plates. But before I go to field between charged particles and plates, sometime we will be told to sketch the field where the negative charge is they are not of the same magnitude. For example, this is Q1, this is Q2, such that Q1 is greater than Q2 in terms of magnitude. So that means if Q1 is greater than Q2, when we are drawing the fields, they are going to change slightly. That one there, and that one there. Two things are going to change. One, this one is going to have more number of field lines. The pattern may remain slightly the same, the neutral position of the neutral point is going to change. It's not going to be in the middle. Are you noting that? Here, the position of the neutral point was in the middle because they were having the same number of field lines and therefore the same charges. But if this one, if Q1 is greater than Q2, the position of the neutral point will drift towards a charge with less amount of charge, or less quantity of charge. So the position of the neutral point will change, the direction will be maintained. The number of field lines has to show that this one is greater. In fact, when we are marking, we count them. We count 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5. Then that means this is smaller. The second marking point is the position of our neutral point. If it is in the middle, then that mark is lost. We'll be giving 4 marks here. The marks we give: 1, direction of the fields. The second mark we give is the pattern, meaning that the shape is given. The third mark we give is position of neutral point. And the last one, which you pay greater attention, is number of field lines. So if we decide to give you this pattern 2 marks, our concentration is going to be on these ones. We may decide to give half a half, and then we give you 2 marks. Such that when you draw wrong field lines, wrong direction, you don't say that you don't lose anything. You lose everything. You get the others, and then you only skip at those ones that you have not brought up. Okay. Now we go to patterns and plates. Field charged points and plates. The plates have only 2 charges: positive and negative charges. Now the charges also are having only 2. It is the pattern that is going to remain the same. Now we go sketches. If we use a negatively charged plate and then a positive charge on the body, definitely these are opposite in charge. By law of electrostatics, like charges attract and unlike charges repel, so this one will be attracted to the plate. And therefore the field is going to be. Now you realize this is the easiest part of electrostatics because it does not involve calculation and it is only using one law. Only one law. Like charges attract and like charges. Unlike charges attract, like charges repel. Only. The same thing is going to happen with the negative charge. This is a positively charged plate, and then this is a negative, and then the pattern will remain the same because they are opposite charges, but the direction will change. So this will now be towards the negative ones. So the pattern will change, the direction will change, but the pattern will remain the same. Now what if they are of the same charge? This one, both positive, this is positive and that one is positive, so like charges repel. So that means this field is now going to move away, and also this one moves away, and the pattern is maintained like that. The neutral point is created, where the resultant pattern is 0. Same thing if it is positive, it is we decide to bring a negative and a negative. Negative, negative, here, the pattern is going to remain the same, the direction is the one going to change. Because this is a negative plate, we expect the direction to be towards the plate, and also this one to be towards the plate. Away, sorry, towards it. So the shape remains the same. You can see that the shape here and the shape there are the same, the position of the neutral point. But still, the magnitude counts. If the plate is having more charge than the point charge, the position of the neutral point will shift. It may not be at the center as we have tried to indicate in the sketches that you see below. Now we could also have plates and plates without point charges. We could also have, for example, positive plate and a negative plate. Here we are going to be having a uniform field moving from plate, from the upper plate to the downer plate, depending on the direction. And the edges, it is going to be slightly curved. So we are bearing the law. Or we could have a positive plate and a positive plate. Positive plate and a positive plate. These ones are going to repel, creating position of the neutral point, depending on how many field lines. The number of field lines dictate the quantity of charge that is present. There we have a neutral point. The same thing will happen if you use a negative charge. But sometimes all these sketches you may sketch using only two. But we may have more than one case. For example, you will be given three charges. One is positive, another one is negative, another one is positive. So you may not just make a framework that they should all be two on opposite side. You can have a pattern like that. You say sketch the electric field pattern around the charges as you see. The principle is the same. You will know we are going to be having attraction, and then here we are going to be having repulsion. So since it is repulsion, attraction, then we expect this one to move like this. Remember the characteristics of our fields. We say the fields repel each other sideways. They move from positive to negative. Now here it is also negative. That means this is going to also attract. So expect something like this. Now here we expect repulsion. If they are of the same magnitude of charge, then the position of the neutral point is going to be in the middle. So that one is going to be there, and that one there. So you see different patterns like that. Something of this sort. So field positive, direction moves away. Field positive, direction moves away. Field negative, it moves towards. And that is the resultant magnetic field. Resultant electric field. So the field pattern which you may come up with, it could be like that. And sometimes we may be given like the one we gave you in an activity here down. It was saying, and that is the final activity, and we are concluding the lesson. Sketch electric field pattern between two positively charged points near a negatively charged plate. You see this? Two, two positively charged points near a negative plate, meaning that there is a positive charge here.
It is this one.
Hmm?
It is this one. Positively charged.
Yes, two positively charged
And
and then a negatively charged plate. Two positive and then a negatively charged what? Plate. So you can see the two here are repelling and then they are attracted. Remember, they have to reach at the surface at right angle. So that means here we'll be having one direct here at right angle. Another one here at right angle. Something happens here at right angle. You can also extend something of this kind. But here we are going to be having repulsion. So that is the position of the neutral point. The directions have to be catered for. Neutral point. That's a neutral point. So that is the shape. So sometimes you may not cram the way we have given it in the notes. You need to see how the question phrases it and then you answer accordingly. So we are concluding by allowing you to work out this activity at your convenient time. It is only one number. We have done most of the numbers. I think that one will be sufficient for the conclusion text, especially in the COVID period. Assalamu alaikum wa rahmatullahi wa barakatuh.